How far can beauty travel? What does a galaxy look like up close? Why do some shine, while others vanish into darkness? Are we seeing the past, or something else entirely? And why can't we look away? Out there, beyond the reach of our own galaxy, lies a silent masterpiece, scattered across the fabric of space. Each swirl, each spark, each faint glow is a story from another corner of the universe. Somewhere out there, a galaxy spins, silent, unobserved. Its light has traveled for billions of years, only now brushing the edges of our awareness. Tonight, we follow that light. Not for science alone, but for wonder. This is not just about distance, it is about beauty. It is about time. It is about what happens when you look into the past and find something too beautiful to forget. Imagine yourself floating in the vastness of space, untethered from Earth, drifting among the stars. The darkness around you is not empty, but filled with ancient stories told in light. Every pinpoint of brightness carries a message from somewhere far away, somewhere that existed long before our planet formed. As you drift further from the familiar constellations, the darkness deepens. But then, something appears. At first, it might seem like a smudge, a blur against the perfect black. But as you draw closer, this smudge transforms. It unfolds like a flower opening in slow motion, revealing itself as a collection of billions of stars, gas, and dust, all moving together in a cosmic dance that began before our solar system was born. This is a galaxy, not just any galaxy, but one whose light set out on its journey when life on Earth was still learning to crawl from the oceans. The photons that now touch your eyes have crossed a distance so vast that the human mind struggles to comprehend it. They have traveled for millions, sometimes billions of years, carrying with them the image of a cosmic structure that may no longer exist as we see it. The light from Andromeda, our closest galactic neighbor, began its journey 2 million years ago, when our ancestors were first learning to use stone tools. The light from the Whirlpool galaxy started traveling toward us 23 million years ago, when Earth was cooling from a warm period, and the first apes were beginning to appear. And the light from galaxies at the edge of our observable universe has been traveling since the first stars were born, over 13 billion years ago. When we look at galaxies, we are looking through windows in time, windows that show us not just where these cosmic islands are, but when they were. Each galaxy is a moment preserved in light, a snapshot of a universe that was delivered to us across the vast emptiness of space. As darkness falls and your mind begins to quiet, consider this miracle. The light entering your eyes tonight has crossed chasms of space so immense that we had to invent new measurements to describe them. Light years, millions of light years, billions of light years. Distances that reduce our entire planet to less than a speck of dust. Yet despite this immensity, despite the cold vacuum between worlds, beauty finds its way to us. Through telescopes that extend our vision, through instruments that translate invisible wavelengths into colors our eyes can comprehend, we witness splendor that would otherwise remain forever hidden. Tonight, we will journey together through the most beautiful structures in our universe. We will see spirals that spin with mathematical precision, their arms stretching out like cosmic pinwheels frozen in time. We will witness colors that tell stories of stellar birth and death, of elements forged in the hearts of stars and scattered across galaxies. We will observe shapes crafted by gravity's patient hand over timescales that make mountains seem ephemeral and oceans seem new. The galaxies we will explore are more than scientific curiosities. They are nature's masterpieces, painted across the canvas of space-time with brushstrokes millions of light years long. They remind us of how small we are, yet how fortunate to exist in a universe capable of such beauty. They remind us that even in vast emptiness, patterns emerge, order forms, light persists. In the silence of the night, as the world around you fades, let these distant galaxies be your companions. Their light has crossed unimaginable distances to reach us. Their forms have evolved over billions of years. Their stories began long before our planet formed, and will continue long after our sun has burned out. There is something profoundly comforting in this cosmic perspective. Our troubles, however overwhelming they might seem, are temporary ripples in the flow of time. Our lives unfold against the backdrop of a universe whose beauty and complexity dwarf our understanding. And yet, here we are, able to appreciate it, able to wonder, able to feel both insignificant and deeply connected to everything that exists. As your eyes grow heavy and your breathing slows, know that you are part of this cosmic story. The elements in your body were forged in the hearts of stars that died billions of years ago. The carbon in your cells, the iron in your blood, the calcium in your bones, all were created in stellar furnaces and scattered across space when those stars exploded. We are, quite literally, made of stardust. The universe is not just something we observe, it is something we are. So close your eyes, breathe deeply, and let us begin our journey to places we will never touch, but whose beauty has touched us across billions of years of darkness. To the spirals and clusters, the rings and clouds, the galaxies that fill our universe with light and form and color. To the most distant and most beautiful things we will never see with our own eyes, but which we can visit in our minds as we drift towards sleep. Not all spiral galaxies are created equal. Astronomers classify them based on the tightness of their spiral arms and the size of their central bulge. Some, like NGC 4565, are called flocculent spirals because their arms are broken and feathery, rather than smooth and continuous. Others, like NGC 1300, have grand design spirals with well-defined, sweeping arms that can be traced for great distances. Our own Milky Way falls somewhere in between, with several major arms and numerous smaller spurs and branches. One of the most perfect spiral galaxies known is NGC 6814, sometimes called the Little Sombrero. When viewed from Earth, we see it almost exactly edge-on, revealing the thin disk of the galaxy silhouetted against the night sky. A dark lane of dust runs precisely along the galaxy's equator, dividing it into two symmetric halves. This dust lane is composed of tiny particles similar to soot, mixed with molecules of hydrogen, carbon monoxide, and other compounds. These dust grains absorb and scatter blue light more effectively than red, which is why the lane appears dark and why distant galaxies often appear redder than they actually are, a phenomenon called interstellar extinction. The more we study spiral galaxies, the more we realize how dynamic they are. Far from being fixed structures, they are constantly evolving. Stars move, gas flows, new stars form, and old stars die. The spiral pattern itself shifts over time, rotating around the galaxy at a different rate than the stars themselves. This means that stars move into and out of the spiral arms as they orbit the galactic center, much like cars moving through a traffic jam on a highway. As we observe these majestic structures from our tiny planet, there is something profoundly humbling about their scale and beauty. A single spiral galaxy contains hundreds of billions of stars, each potentially hosting planets of its own. The light we see from them has traveled for millions or even billions of years across the void of space, carrying with it the image of these galaxies as they were long before humans walked the Earth. In a very real sense, to look at a distant galaxy is to look back in time, to see a chapter of cosmic history written in light. The balance that creates spiral galaxies is not permanent. Over enormously long periods, many spiral galaxies will eventually transform into elliptical galaxies through mergers with other galaxies. Our own Milky Way is on a collision course with the nearby Andromeda Galaxy, another magnificent spiral. In about 4.5 billion years, these two spirals will begin to merge, their delicate structures disrupted by gravitational forces. After several passes through each other, they will settle into a single, larger elliptical galaxy, their spiral arms lost to the chaos of collision, but their stars continuing their cosmic journey in a new configuration. As your eyelids grow heavy, imagine the slow, stately rotation of these cosmic pinwheels. A single rotation of a galaxy like our Milky Way takes more than 200 million years. The last time our solar system was in this exact position relative to the galaxy's center, dinosaurs were just beginning to walk the Earth. By the time we complete another full orbit, humanity in its current form will almost certainly be gone, replaced by whatever we evolve into, if we survive at all. Yet the galaxy will continue its patient rotation, indifferent to our brief presence. In the quiet darkness, let the image of these spirals carry you towards sleep. Their balanced symmetry, their patient turning, their perfect union of order and chaos. Let their beauty remind you that even in a universe of incomprehensible vastness, patterns emerge, structure forms, harmony exists, and sometimes that harmony takes the shape of a spiral, painted across the canvas of night in billions of points of light. Color in galaxies tells us about time. The bluest regions are the youngest, places where stars have recently formed. The reddest regions are the oldest, populated by stars that have been shining steadily for billions of years. This connection between color and time allows astronomers to reconstruct a galaxy's history from a single snapshot, reading its biography from the hues of its stars. It's like looking at a forest and seeing seedlings, mature trees, and ancient giants all at once, the entire life cycle visible in a single glance. As you rest in the darkness, imagine these colors washing over you, the golden glow of ancient stellar cores, the azure brilliance of massive young stars, the rose-pink nebulae where new suns are being born, the ruddy flare of a dying supergiant. These colors are not just beautiful, they are informative. They tell stories of creation and destruction, of youth and age, of energy and quiet persistence. They are the palette with which the universe paints its grandest structures, a cosmic language written in light for anyone patient enough to learn its grammar. In the stillness of night, as sleep approaches, remember that the darkness above us is not truly dark. It is filled with color beyond imagining, a chromatic symphony playing across billions of light years. And we, on our tiny world, have somehow developed the ability to see this symphony, to decipher its meaning, and to feel wonder at its beauty. The colors of galaxies remind us that the universe is not just vast and ancient, but vibrant and alive with processes of transformation that have continued unabated since the first stars began to shine. For some extremely distant galaxies, the light we detect left its source when the universe was so young that the galaxies themselves were still in the process of forming. These protogalaxies appear as small, irregularly shaped blobs of intense star formation. Their chaotic appearance reflects a time before gravity had fully shaped them into the ordered structures we see today. When we observe these systems, we are witnessing galactic birth, the first chapters in a cosmic story that continues to unfold across billions of years. The most distant galaxy currently known, HD 1, appears to us as it was just 330 million years after the Big Bang. The universe was less than 3% of its current age when the light we now detect left this galaxy. In the more than 13 billion years since, this galaxy has continued to evolve and change in ways we cannot observe. The image we see is a baby picture of a cosmic structure that, if it still exists, is now an ancient elder among galaxies. There is something profoundly moving about this relationship between light, distance, and time. Every photon that reaches our telescopes from a distant galaxy has traveled through the void of space for millions or billions of years, carrying with it a message from the cosmic past. These messages arrive continuously, a stream of information about how the universe looked at different stages of its evolution. By collecting and interpreting this information, we piece together the biography of the cosmos, understanding not just how it appears now, but how it has changed over time. As you drift towards sleep, consider the light that surrounds you. Some of it left the lamp beside your bed a few nanoseconds ago. Some left the distant streetlight a few microseconds ago. The light from the moon took 1.3 seconds to reach your window. And perhaps, through that same window, a few photons are arriving from Andromeda after a journey of 2.5 million years. All of these messengers from different eras coexist in your room, each carrying information about its source from the moment it departed. The light from distant galaxies reminds us that the present moment is an illusion. What we perceive as simultaneous is actually a collage of different times, near and far, recent and ancient. The universe we observe is not a single snapshot, but a vast panorama of cosmic history, with each distance revealing a different chapter in the ongoing story of creation. In this way, astronomy becomes a form of time travel, allowing us to witness events that occurred long before our species, our planet, or even our sun existed. In the quiet darkness, as consciousness begins to fade, imagine the countless photons that have crossed vast gulfs of space and time to reach our tiny world. Some began their journey when the first galaxies were forming. Others left their sources when dinosaurs roamed the Earth. Each carries a fragment of cosmic history, preserved in the amber of light's finite speed. And we, on our small planet orbiting an ordinary star, have somehow developed the ability to capture these messengers from the past and decode their ancient stories. In this way, through the persistence of light, the universe remembers itself. While spiral galaxies might be the most recognizable cosmic structures, they represent just one expression of gravity's artistic hand. The universe is filled with galaxies of astonishing variety, each shape telling a different story of formation and evolution. Tonight, we explore the diverse morphology of galaxies, from perfect ellipticals to chaotic irregulars, from ring-shaped anomalies to colliding systems frozen in cosmic dance. Let us begin with the elliptical galaxies, cosmic clouds of stars that lack the dramatic spiral structure of their more photogenic cousins. Messier 87 in the Virgo cluster is one of the largest and brightest examples. Unlike the flat disks of spiral galaxies, ellipticals are three-dimensional clouds of stars, ranging from nearly spherical to highly elongated shapes. Their stars move in random orbits rather than the organized circular paths found in spirals. This gives ellipticals a smooth, featureless appearance, like luminous cotton balls floating in the darkness of space. Despite their simple appearance, elliptical galaxies are cosmic titans. The largest, called giant ellipticals, can span over 1 million light-years and contain trillions of stars. IC 1101 in the constellation Virgo is one such giant. If placed where our Milky Way is, it would engulf our entire local group of galaxies. These behemoths form primarily through mergers, cosmic collisions where two or more galaxies combine over billions of years. Each merger erases more of the original structure, eventually producing these smooth, featureless systems dominated by old, red stars. They are cosmic senior citizens, their star forming youth long behind them. Not all ellipticals are giants. At the other end of the scale are dwarf elliptical galaxies, cosmic minnows, that may contain just a few million stars. These diminutive systems often orbit larger galaxies as satellites. Our own Milky Way has several such companions, including the Fornax dwarf and the Sculptor dwarf. Despite their small size, these galaxies play an important role in cosmic evolution. They are the building blocks from which larger galaxies form, and studying them gives us insight into the earliest stages of galaxy formation. Between the extremes of spirals and ellipticals lie the lenticular galaxies, cosmic hybrids that combine features of both types. NGC 4594, sometimes called the Sombrero Galaxy due to its distinctive appearance, is a famous example. Lenticulars have the disk shape of spirals but lack their distinctive arms. Instead, their stars are distributed more like those in ellipticals, with little ongoing star formation and few young blue stars. They represent a transitional form, possibly spirals that have lost their gas and can no longer form new stars, slowly aging toward elliptical status. Among the most captivating galactic forms are the ring galaxies, cosmic structures that seem almost too perfect to be natural. Hoag's object, discovered in 1950 by astronomer Arthur Hoag, is the most striking example. It consists of a yellow core of older stars, surrounded by a nearly perfect ring of young blue stars, with apparently nothing connecting the two components. This bizarre structure likely formed when a smaller galaxy passed directly through the center of a larger one, creating a ripple effect similar to a stone dropped in a pond. The expanding density wave triggered star formation as it moved outward, creating the distinctive blue ring we observe today. The Cartwheel Galaxy shows us another variation on this theme. Its ring structure is less perfect than Hoag's object, with spokes of stars connecting the outer ring to the inner core. This system still shows the scars of its violent formation, with the ring visibly offset from the galaxy's center. Astronomers estimate that the collision that created this structure occurred about 400 million years ago. The ring is still expanding outward at roughly 217 miles per second, continuing the cosmic ripple effect triggered by the ancient collision. Some of the most dramatic galactic shapes emerge during interactions between galaxies. The Mice galaxies, formerly catalogued as NGC 4676, show us two spiral galaxies in the early stages of collision. Gravitational forces have already begun to distort their shapes, pulling out long tails of stars like cosmic streamers. These tidal tails can stretch for hundreds of thousands of light years, containing billions of stars torn from their original galaxies by gravitational forces. Over the next few 100 million years, these two galaxies will continue their cosmic dance, eventually merging into a single, larger system. Further along in the merger process are the antennae galaxies, NGC 4038 and NGC 4039. These two spirals are more deeply engaged in their gravitational embrace, their original structures significantly distorted and partially merged. Huge plumes of stars extend from the collision zone, giving the system its insect-like appearance. In the region where the two galaxies overlap, gas clouds are being compressed, triggering an extraordinary burst of star formation. Over 1,000 star clusters have formed in this cosmic collision zone, each containing up to 1 million young stars. It is creation, born from destruction, a theme that repeats throughout cosmic evolution. At the far end of the interaction spectrum is Messier 82, sometimes called the Cigar Galaxy, due to its elongated shape. This system shows us the aftermath of a galactic merger that occurred perhaps 1 billion years ago. The original spiral structures have been completely erased, replaced by a chaotic distribution of stars and dust. At the galaxy's center, the intense compression of gas has triggered one of the most powerful starbursts known, with stars forming at a rate 10 times higher than in our Milky Way. The entire galaxy glows with the light of these new stars, a cosmic phoenix risen from the ashes of its progenitors. Not all galaxies fit neatly into classification schemes. The irregular galaxies show us cosmic structures with no discernible symmetry or organized structure. The large and small Magellanic Clouds, satellite galaxies of our Milky Way visible from the southern hemisphere, are classic examples. These systems appear as chaotic collections of stars, gas, and dust, with regions of intense star formation scattered throughout. Many irregulars are small systems that have been gravitationally disturbed by larger neighbors. Others may be young galaxies still in the process of settling into more organized forms. IC10 in the constellation Cassiopeia shows us an irregular galaxy in the throes of extraordinary star formation. Despite its relatively small size, it is producing new stars at a rate that would exhaust its gas supply in just a few 100 million years, a mere moment in cosmic time. This frenzied activity may have been triggered by a close encounter with another galaxy, or by gas falling into the system from intergalactic space. Whatever the cause, the result is a cosmic fireworks display of star birth, with no organized structure to contain it. In the most extreme environments, we find galaxies with shapes dictated by external forces. In dense galaxy clusters, where hundreds or thousands of galaxies orbit within a common gravitational well, strange distorted forms emerge. As galaxies move through the hot, thin gas that fills these clusters, they experience a form of cosmic headwind that can strip away their own gas, creating long tails that stream behind them like cosmic contrails. These jellyfish galaxies, as astronomers call them, show us systems in the process of transformation, their shapes recording the environmental pressures they experience. The galaxy Perseus A shows us yet another unusual form. This system appears to have multiple layers of shells surrounding its center, like a cosmic onion. These concentric structures likely formed when a smaller galaxy was captured and gradually torn apart by the larger system's gravity. Each shell represents material from the captured galaxy that has spread out into a roughly spherical layer, preserving a record of this cosmic cannibalism. At least half of all large elliptical galaxies show such shells, evidence that galactic mergers are a common occurrence in cosmic evolution. Perhaps the strangest galactic shapes emerge in the presence of supermassive black holes. Some active galaxies, powered by black holes feeding on surrounding material, generate enormous jets of charged particles that extend far beyond the visible borders of the galaxy itself. Centaurus A shows us this phenomenon in dramatic form, with jets extending more than 1 million light-years from the galaxy's center. These structures, invisible in optical light, but prominent in radio and X-ray wavelengths, reshape the galaxy's appearance and influence its evolution by injecting enormous amounts of energy into surrounding space. The diversity of galactic forms reminds us that the universe is not static but dynamic, a place where gravity sculpts matter into an endless variety of shapes. Each configuration tells a story of formation and evolution, of interaction and transformation. Some shapes reflect internal processes, the natural development of self-gravitating collections of stars. Others record external influences, the gravitational pull of neighboring galaxies, or the pressure of intergalactic environments. Together, they show us the many faces that galaxies can wear as they evolve through cosmic time. As you rest in the darkness, imagine these diverse cosmic structures floating in the void of space. The majestic spirals, with their elegant arms. The smooth, featureless ellipticals like cosmic riverstones worn smooth by time. The bizarre rings with their perfect symmetry. The chaotic beauty of colliding systems frozen in gravitational dance. Let your mind drift among these shapes, each one a different expression of gravity's patient hand shaping the stuff of stars. In their diversity is a reminder that even with simple physical laws, complexity and beauty emerge when matter interacts across billions of years of cosmic time. In the quiet, as sleep approaches, remember that these shapes are not merely aesthetic curiosities, but chapters in the story of cosmic evolution. The irregular dwarf that will one day be consumed by a larger neighbor. The spiral destined to collide with another and form an elliptical. The ring that will gradually lose its perfect form as its stars continue their orbits. Each shape we observe is just a moment in an ongoing process, a single frame in a cosmic film that has been running for 13.8 billion years. And we, on our tiny planet, have somehow developed the ability to read this film, to understand these shapes, and to feel wonder at their beauty and meaning. When we gaze at individual galaxies, we see cosmic islands, vast collections of stars separated from each other by even vaster gulfs of space. But galaxies are not solitary wanderers in the cosmic ocean. They gather together, drawn by mutual gravity into groups, clusters, and superclusters, creating a cosmic web that spans the observable universe. Tonight, we explore these gatherings of galaxies, the largest structures known to exist. Our own Milky Way is part of what astronomers call the local group, a collection of more than 50 galaxies bound together by gravity. Most of these are dwarf galaxies, cosmic minnows containing just a few million stars. But the local group also includes two other major galaxies besides our own. The Andromeda Galaxy, slightly larger than the Milky Way, lies about 2.5 million light-years away. The Triangulum Galaxy, somewhat smaller than our own, is about 3 million light-years distant. Together with their satellite galaxies, these three spirals form the heart of our galactic neighborhood. The local group spans about 10 million light-years across, a vast expanse by human standards, but modest on the cosmic scale. The galaxies within it move in relation to each other, drawn together by gravity into a slowly contracting configuration. In about 4.5 billion years, the Milky Way and Andromeda will begin to merge, their majestic spiral structures gradually disrupted by gravitational forces as they pass through each other multiple times. Eventually, they will settle into a single, larger elliptical galaxy that astronomers have whimsically named Milkomeda. Our descendants, should humanity or its offshoots still exist, will look up at a very different night sky, dominated by the scattered stars of this merged system, rather than the band of the Milky Way we see today. Beyond our local group lies the Virgo cluster, the nearest large cluster of galaxies, about 54 million light-years away. This cosmic metropolis contains more than 1,000 galaxies, from giant ellipticals to graceful spirals to tiny dwarfs. At its heart lies Messier 87, also known as Virgo A, one of the most massive galaxies known. This giant elliptical contains several trillion stars and harbors. At its center, a supermassive black hole with the mass of 6.5 billion suns. Unlike the relatively sparse local group, the Virgo cluster is dense enough that galaxies within it frequently interact and merge, gradually building larger systems from smaller components. The Virgo cluster is not isolated in space, but forms part of the larger Virgo supercluster, a collection of galaxy clusters and groups spanning more than 110 million light-years. This supercluster contains at least 100 galaxy clusters and thousands of individual galaxies, all moving within a common gravitational field. Our local group resides near the edge of this supercluster, slowly orbiting its center over billions of years. The Virgo supercluster represents one of the major nodes in the cosmic web, a concentration of matter surrounded by relatively emptier regions of space. Even more impressive is the Coma cluster, located about 320 million light-years away in the constellation Coma Berenices. This rich cluster contains thousands of galaxies concentrated in a region just 20 million light-years across. The density of galaxies in the Coma cluster is so high that if we lived within it, our night sky would be filled with galaxies appearing larger and brighter than the stars we see from Earth. These galaxies move through the cluster at speeds of thousands of kilometers per second, occasionally passing close enough to gravitationally influence each other. Over billions of years, these interactions gradually transform the cluster's population, with spiral galaxies being disrupted and converted into ellipticals through mergers and tidal stripping. Between these dense clusters lie vast filaments of galaxies, cosmic highways stretching tens or even hundreds of millions of light-years. The Perseus-Pisces supercluster shows us one such filament, a chain of galaxy clusters and groups extending more than 300 million light-years across space. Thousands of galaxies lie along this structure, strung like pearls on a cosmic necklace. These filaments form the visible tracer of the cosmic web, the largest structure in the universe. Perhaps the most awe-inspiring view of the cosmic tapestry comes from large-scale surveys that map hundreds of thousands of galaxies across billions of light-years. The Sloan Digital Sky Survey has created such a three-dimensional map, revealing the bubble-like structure of the universe on the largest scales. Galaxies are not distributed randomly, but form a sponge-like pattern, with dense walls and filaments surrounding vast, relatively empty regions called voids. This cosmic web formed from tiny fluctuations in the density of the early universe, amplified over billions of years by gravity's relentless pull. The largest void known, the Botas void, spans 330 million light-years yet contains almost no galaxies. This cosmic desert is large enough to contain 30,000 galaxies like the Milky Way, yet fewer than 60 have been detected within it. The contrast between these empty regions and the dense filaments that surround them creates the distinctive texture of the cosmic web, a pattern that emerged from the interplay of gravity, dark matter, and the expansion of space itself. At the intersections of cosmic filaments, we find the most massive structures known, the galaxy superclusters. The Shapley supercluster, about 650 million light-years away, is one of the largest such structures, containing over 8,000 galaxies in a region, spanning 100 million light-years. The combined mass of this supercluster is equivalent to more than 10 million billion suns, creating a gravitational pull so strong that it influences the motion of galaxies across a significant fraction of the observable universe. Our own Milky Way, along with the entire local group and Virgo supercluster, is being pulled towards Shapley at hundreds of kilometers per second, a cosmic migration that will continue for billions of years. When we observe very distant galaxy clusters, those billions of light-years away, we see them as they were when the universe was much younger The cluster, max J1149.5 plus 2223, more than 8 billion light-years distant, shows us how these cosmic structures appeared when the universe was less than half its current age. Despite the passage of time, the basic hierarchical pattern of the cosmic web was already established. Galaxies had already gathered into clusters, and these clusters were already arranged along filaments. The overall structure of the cosmic web appears to be one of the most fundamental and enduring patterns in nature. One of the most extraordinary windows into the cosmic tapestry is the Hubble Ultra Deep Field, an image created by pointing the Hubble Space Telescope at a seemingly empty patch of sky for a total exposure time of more than 11 days. This small section of sky, covering an area less than 1/10 the width of the full moon, revealed nearly 10,000 galaxies at various distances. Some of these are seen as they were just a few hundred million years after the Big Bang. The image shows galaxies of all shapes, sizes, and colors, scattered across billions of light-years of space and time. It is a core sample of the universe, revealing the density and diversity of galaxies throughout cosmic history. The James Webb Space Telescope has pushed our view even deeper with its first deep field image, showing galaxies as they were more than 13 billion years ago. In this small patch of sky, equivalent in size to a grain of sand held at arm's length, thousands of galaxies are visible. Some appear as they were when the universe was just 4% of its current age. The image reveals not just individual galaxies, but entire clusters already formed in the early universe, challenging our understanding of how quickly cosmic structures can assemble. When we step back and consider the universe as a whole, we find a tapestry of astonishing complexity and scale. From our position within the Milky Way, we can observe approximately 2 trillion galaxies within our observable universe. Each of these galaxies contains billions or even trillions of stars, many with their own planetary systems. The sheer number of cosmic structures defies comprehension, yet all follow patterns dictated by the same physical laws that operate here on Earth. Gravity, electromagnetism, and the other fundamental forces work across cosmic scales to create order from chaos, structure from uniformity. This cosmic tapestry is not static, but evolving. The expansion of the universe gradually increases the distances between galaxy clusters, while gravity pulls the galaxies within each cluster closer together. Over vast spans of time, this dual process will transform the visible universe. Billions of years from now, the cosmic web will consist of isolated islands of merged galaxies, each containing the combined stellar populations of what were once separate systems. The filaments and voids that define the current cosmic web will stretch beyond observability, leaving each island effectively alone in its own observable universe. There is something profoundly humbling in contemplating the cosmic tapestry. Our entire Milky Way galaxy, with its 400 billion stars, is just one node in this vast network. Our solar system is less than a pixel in the cosmic image. Yet through observation and analysis, we have mapped structures spanning billions of light years. We have traced the evolution of cosmic architecture from the earliest epochs to the present day. And we have discovered that despite its immense scale and complexity, the universe follows patterns that we can understand and predict. As you drift towards sleep, imagine this infinite tapestry of galaxies stretching in all directions, clusters and superclusters surrounded by vast cosmic voids, filaments of galaxies spanning hundreds of millions of light years, individual galaxies, each containing billions of stars, appearing as mere points in this grand cosmic web. Let the scale and beauty of this structure carry you toward dreams. In its immensity, there is not terror, but perspective. In its complexity, not confusion, but wonder. The cosmic tapestry reminds us that we are part of something vastly larger than ourselves, a universe of such scope and grandeur that even our most powerful telescopes can reveal only a fraction of its splendor. In the quiet darkness, as consciousness begins to fade, remember that you too are woven into this cosmic fabric. The atoms in your body formed in the hearts of stars that died billions of years ago. The matter that makes you once flowed through the cosmic web, guided by gravity into the galaxy, star, and planet you now call home. You are not separate from this vast structure, but an integral part of it, a collection of stardust that has, for a brief moment in cosmic time, taken the form of a conscious being capable of contemplating the universe that created it. Multi-wavelength astronomy, combining observations from different parts of the electromagnetic spectrum, provides the most complete picture of distant galaxies. Each wavelength reveals different components and processes. Ultraviolet light shows the youngest, hottest stars. Visible light reveals the overall stellar population. Infrared penetrates dust clouds to show hidden structure and older, cooler stars. Radio waves trace cold gas and magnetic fields. X-rays highlight the most energetic phenomena. By synthesizing all these observations, astronomers construct a comprehensive understanding of galaxies that far exceeds what any single instrument could provide. The future promises even more powerful instruments that will further extend our cosmic vision. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will combine a Hubble-sized mirror with a field of view 100 times larger, allowing it to survey vast regions of the sky in unprecedented detail. Ground-based behemoths like the 30-meter telescope and the European Extremely Large Telescope, with mirrors 100 feet across or larger, will collect enough light to study the very first galaxies that formed after the Big Bang. These instruments will continue to push the boundaries of our knowledge, revealing galaxies even more distant and ancient than those we can currently observe. What makes these technological achievements truly remarkable is that they allow us to study objects we can never visit. The nearest large galaxy beyond our own, Andromeda, is 2.5 million light-years away. Even traveling at the speed of light, it would take us 2.5 million years to reach it. The most distant galaxies we can observe are more than 13 billion light-years away, utterly beyond any conceivable form of physical exploration. Yet through the light they send us, analyzed by instruments of extraordinary sensitivity and precision, we can study their structure, composition, and motion in remarkable detail. As you slip towards sleep, consider the astonishing chain of events that allows us to know these distant realms. Light leaves a galaxy billions of years ago, traversing the expanding space of the cosmos. It encounters no significant matter for almost the entire journey, traveling in an uninterrupted path toward our tiny planet. Here, it enters our atmosphere and is collected by a telescope, either on the ground or in orbit. The telescope focuses this ancient light onto sensitive detectors that register its arrival, photon by photon. Computers process this information, reconstructing an image of the galaxy as it was billions of years in the past. And finally, a human being, a conscious entity assembled from elements created in long-dead stars, observes and interprets this image, understanding something about a place they will never visit and a time long before they existed. In this way, through instruments of remarkable sophistication, we transcend the limitations of our physical bodies. We extend our vision across billions of light years, peering into the cosmic past to witness the grandeur and diversity of distant galaxies. Though we cannot touch these cosmic structures, though we will never walk among their stars, we can know them through the messages they send us in light. And in that knowledge, we find not just scientific understanding, but a sense of connection to the larger cosmos. A recognition that though we are bound to our small planet, our minds can encompass the vastness of creation. The universe has a fondness for spirals. From the tiny swirl of a nautilus shell to the massive arms of galaxies stretching tens of thousands of light years, this pattern repeats itself across scales that defy imagination. Tonight, we begin our journey with perhaps the most elegant of all cosmic structures, the spiral galaxy. Imagine yourself drifting toward a galaxy called Messier 101, better known as the Pinwheel Galaxy. From a distance, it appears as a delicate whirlpool of light against the blackness of space. As you approach, the structure reveals itself in breathtaking detail. The galaxy spans 170,000 light-years from edge to edge, nearly twice the size of our own Milky Way. Its spiral arms sweep outward in perfect logarithmic curves, each one a river of stars flowing through the cosmos. These arms are not solid structures, but patterns of density waves moving through the galaxy's disk. Think of them as cosmic traffic jams, places where stars and gas clouds bunch together as they orbit the galactic center. The compression triggers the birth of new stars, which is why spiral arms often glow with the blue-white light of young, massive stars, and the pink-red hue of hydrogen clouds where stars are still forming. The spiral shape itself is a delicate balance between motion and gravity. Every star in the galaxy is in orbit around the central bulge, where millions of older stars cluster together in a spherical collection. Closer to the center, stars complete their orbits faster than those at the edges. This differential rotation should wind the spiral arms tighter and tighter until they disappear. Yet the arms persist, maintained by density waves that move through the galactic disk like ripples on a pond. Consider the galaxy NGC 1618, often called the Phantom Galaxy. Its perfect spiral structure seems almost too precise to be natural, its arms unwinding with mathematical elegance. Viewed face-on from Earth, we can see how the dust lanes trace the inner structure of the spiral, dark ribbons against the glow of starlight. In the gaps between these dust lanes, pockets of intense star formation create blue knots of light, stellar nurseries where hundreds of stars are being born even as we observe them from afar. Our own home, the Milky Way, is also a spiral galaxy, though we cannot see its full structure from our position within one of its arms. We are cosmic neighbors who have never seen each other's faces. Like inhabitants of a vast city who have never seen its skyline, we can only imagine the full splendor of our galactic home based on what we can observe of similar galaxies throughout the universe. If we could somehow rise above the plane of the Milky Way and look down upon it, we would see a majestic spiral with 4 major arms sweeping outward from a central bar of stars. Our Sun would be just one point of light among 400 billion others, located in a minor arm called the Orion Arm, about 26,000 light-years from the galactic center. The motion of these spiral arms creates a kind of cosmic music too, a harmony of gravitational interactions playing out over millions of years. Stars do not simply orbit, they oscillate up and down through the galactic plane, creating a 3-dimensional dance of incredible complexity. If we could somehow compress billions of years into a few minutes, we would see the galaxy not as a static structure, but as a living, breathing entity, pulsing with the rhythms of stellar birth and death. In the galaxy Messier 74, we can observe another fascinating feature of spiral galaxies: the presence of a central bar. This straight formation of stars cuts across the galactic core like the handle of a cosmic umbrella, with spiral arms unfurling from its ends. Nearly 2/3 of all spiral galaxies have these bars, including our own Milky Way. They form through gravitational interactions and help channel gas toward the center of the galaxy, fueling bursts of star formation and feeding the supermassive black hole that lurks at the galaxy's heart. The variety among spiral galaxies is astonishing. Some, like Messier 99, have arms so tightly wound they almost form a ring around the core. Others, like NGC 2841, have loose, open arms that seem to lazily reach out into intergalactic space. Some spirals are perfectly symmetric, while others show signs of past collisions that have distorted their shape, creating asymmetric arms or tidal tails of stars pulled out by gravitational interactions with passing galaxies. Perhaps the most beautiful spiral galaxy visible from Earth is Messier 81, the famous Bode's galaxy. Its structure combines the elegance of twin spiral arms with the additional complexity of numerous small branches and filaments. Dark dust lanes trace the inner edges of the arms, while bright blue star clusters punctuate the outer edges. At its center glows the yellow light of billions of older stars, crowded together in a bulge that contains the mass of millions of suns. As you gaze at these cosmic pinwheels, notice how they embody a kind of frozen motion. The light reaching us has traveled for millions of years, showing us these galaxies not as they are now, but as they were when that light began its journey. The spiral arms we see may have rotated significantly since then. Stars have died and new ones have been born, yet the overall pattern persists. There is something profoundly peaceful in this persistence, this continuity of form across vast gulfs of time and space. The spiral is not just a shape, but a story of balance. Gravity pulls inward, trying to collapse the galaxy into its center. Rotational momentum pushes outward, trying to fling stars away into intergalactic space. Between these competing forces, the spiral emerges, a perfect equilibrium written in stars. It is a reminder that even in the cold vacuum of space, beauty can arise from the interplay of fundamental forces. In the grand catalogue of spiral galaxies, few are as mesmerizing as NGC 1300, sometimes called the Southern Pinwheel. From our vantage point, we see it nearly face-on, revealing the full splendor of its spiral structure. Its arms make almost 2 complete turns around the nucleus, creating a hypnotic pattern that draws the eye inward. Along these arms, bright knots mark regions where gas has been compressed, triggering the formation of massive young stars that burn hot and blue. The Whirlpool Galaxy, or Messier 51, offers us a rare glimpse of interaction between 2 galaxies. A smaller companion galaxy is pulling on one of the Whirlpool's arms, stretching it outward and compressing the gas within it, triggering a burst of star formation that appears as a brilliant blue arc. This cosmic dance has been ongoing for hundreds of millions of years and will eventually result in the smaller galaxy being absorbed into the larger one. Such mergers are common throughout the universe and play a crucial role in how galaxies evolve over time. When we look at spiral galaxies through different wavelengths of light, we see different aspects of their nature. In visible light, we primarily see the stars themselves. In infrared, we can peer through the dust to see structures otherwise hidden. In ultraviolet light, the young, hot stars stand out most prominently. And in radio wavelengths, we can trace the vast clouds of hydrogen gas that serve as the raw material from which new stars form. Each view gives us a new appreciation for the complexity of these cosmic structures. The spiral arms themselves are places of extraordinary activity. Within them, massive clouds of molecular hydrogen collapse under their own gravity, fragmenting into smaller and smaller pieces until they form individual stars. The most massive of these stars burn so hot and bright that they exhaust their nuclear fuel in just a few million years, ending their lives in spectacular supernova explosions that enrich the surrounding gas with heavy elements. This enriched material will eventually be incorporated into new stars and planets, continuing the cycle of cosmic recycling that has been ongoing since the first galaxies formed. In the heart of every spiral galaxy lies a supermassive black hole, a cosmic engine with the mass of millions or even billions of suns. In some galaxies, these black holes actively consume matter, creating brilliant centers that outshine the rest of the galaxy. But in most spirals, including our Milky Way, the central black hole is relatively quiet, exerting its influence primarily through gravity rather than radiation. The relationship between these black holes and their host galaxies is one of the great mysteries of modern astronomy, a cosmic chicken and egg problem that scientists are still working to unravel. The arms of spiral galaxies are not just beautiful structures, they are also cosmic timekeepers. Because stars form within these arms, we can use the ages of star clusters to trace the pattern of the spiral over time. The youngest, brightest stars mark the current position of the arms, while slightly older clusters show where the arms were millions of years ago. By studying this pattern, astronomers can determine how quickly the spiral density waves move through the galactic disk, adding a temporal dimension to our understanding of galactic structure. When we think of space, we often imagine a black void, dotted with white points of light. But galaxies are not colorless entities. They are vibrant, multicolored structures whose hues tell stories of stellar birth and death, of temperature and chemistry, of age and evolution. Tonight, we explore the chromatic language of the cosmos, the palette with which galaxies paint themselves against the darkness. Drift with me toward the Andromeda Galaxy, our cosmic neighbor just 2.5 million light-years away. Even to the naked eye, it appears as a smudge of light with a distinctly yellowish core. Through powerful telescopes, this simple smudge transforms into a symphony of color. At its heart glows the golden yellow bulge, composed of billions of older stars similar to our Sun. These stars have exhausted their supply of hydrogen and now burn helium in their cores, shifting their light toward the red end of the spectrum. This golden heart tells us of age and stability, of stars that have shone steadily for billions of years. Spiraling outward from this core, we find the blue-white arms of the galaxy. Here, the color story changes dramatically. This azure glow comes from massive, young stars burning hot and bright. Unlike their older, yellower cousins in the galactic center, these stellar giants are new additions to the galaxy, some just a few million years old. They burn their hydrogen fuel at prodigious rates, reaching surface temperatures of 30,000 degrees Celsius compared to our sun's relatively modest 5,500. This higher temperature shifts their light toward the blue end of the spectrum, creating the striking color contrast between arm and core. But the color palette of galaxies is not limited to yellow and blue. Scattered throughout the spiral arms, particularly in Andromeda's neighbor, the Triangulum galaxy, we find clouds glowing with a distinctive pinkish-red hue. These are vast regions of hydrogen gas, illuminated by the ultraviolet radiation of nearby young stars. The hydrogen absorbs this high-energy light and re-emits it at a very specific wavelength, creating the characteristic color astronomers call hydrogen alpha emission. These cosmic rose gardens are stellar nurseries, the birthplaces of new stars. Their color signals one of the most fundamental processes in the universe, the transformation of gas into stars. Cutting across the gleaming spiral arms of many galaxies are dark lanes of cosmic dust. These are not truly black, though they appear so in contrast to the brilliant stars around them. If we could see them up close, these dust lanes would reveal themselves as clouds of tiny particles, each smaller than a grain of sand, composed of carbon, silicon, and various ices. They absorb and scatter blue light more effectively than red, which is why they appear dark, and why the light from stars behind them appears redder, a phenomenon astronomers call reddening. This is the same process that makes our sunsets red, when light must travel through more of Earth's atmosphere. In galaxies like NGC 6946, sometimes called the Fireworks Galaxy, we occasionally see bright points of reddish-orange light. These are supernovae, the explosive deaths of massive stars. For a brief period, typically lasting a few weeks, a single dying star can outshine an entire galaxy of hundreds of billions of stars. The distinctive color comes from the emission of various elements thrown out by the explosion, particularly iron, sulfur, and calcium. Each supernova enriches the surrounding space with these elements, the building blocks from which future generations of stars and planets will form. The Large Magellanic Cloud, a satellite galaxy of our Milky Way, contains one of the most colorful regions in our local cosmic neighborhood. The Tarantula Nebula glows with an otherworldly palette of reds, pinks, blues, and golds. This vast star-forming region spans more than 1,000 light-years and would be visible from Earth as a prominent patch of light in the night sky if it were as close as the famous Orion Nebula. Its colors reveal an ongoing stellar baby boom, with thousands of massive stars being born within clouds of gas and dust. The most luminous star known, R136, sits at the heart of this nebula, pumping out energy at a rate 10 million times greater than our Sun. When we look at very distant galaxies, those billions of light years away, we often see them through a filter of cosmic reddening. The expansion of the universe stretches the wavelength of light as it travels through space, shifting all colors toward the red end of the spectrum. This cosmic redshift means that the most distant galaxies appear redder than they actually are. By measuring precisely how much the light has been shifted, astronomers can determine how far away these galaxies are and how long ago the light began its journey toward Earth. In some galaxies, the color story takes a dramatic turn when we look beyond the visible spectrum. The galaxy Messier 87 in the constellation Virgo appears fairly ordinary in visible light, a yellowish elliptical galaxy without remarkable features. But when viewed in radio waves or X-rays, this seemingly quiet galaxy reveals jets of energetic particles streaming from its center at nearly the speed of light, extending far beyond the visible borders of the galaxy. These jets are powered by a supermassive black hole feeding on surrounding matter, a process that generates enormous amounts of energy across the electromagnetic spectrum. The Sombrero Galaxy, Messier 104, presents us with a striking contrast of colors when viewed edge-on. Its brilliant white central bulge rises above and below a thin disk of darkness, looking remarkably like its namesake hat. This distinct coloration comes from the different stellar populations within the galaxy. The bulge is dominated by older, redder stars, while the disk contains a mix of stellar ages, along with lanes of light-absorbing dust. The combined effect creates one of the most visually distinctive galaxies in our night sky. In the Cartwheel Galaxy, located about 500 million light-years away in the constellation Sculptor, we see a color palette shaped by cosmic collision. A smaller galaxy once plunged through the center of a larger spiral, creating a ripple effect like a stone dropped in a pond. The resulting ring structure glows blue with the light of massive young stars triggered into formation by the collision. The inner regions maintain the yellow hue of older stars that survived the cosmic encounter. This color contrast tells the story of galactic trauma and recovery, of destruction, followed by a burst of new creation. The colors we see in galaxies are not just aesthetically pleasing, they are functionally informative. Astronomers use these colors to determine a galaxy's age, composition, history, and even its future evolution. A galaxy dominated by blue light is young and actively forming stars, while one that appears primarily yellow or red has exhausted most of its star-forming gas. Galaxies with unusual color patterns often have unusual histories, typically involving interactions with other galaxies. Beyond the range of human vision lie even more colors, invisible to our eyes, but detectable by specialized instruments. In the infrared spectrum, cold dust clouds glow with thermal radiation, revealing structures hidden in visible light. Ultraviolet light traces the hottest, most massive stars and can penetrate dust clouds that block visible light. X-rays reveal the most energetic processes, such as material falling into black holes or superhot gas in galaxy clusters. Radio waves map out the cold hydrogen gas that serves as fuel for future star formation. Each wavelength adds a new layer to our understanding of these cosmic structures. The James Webb Space Telescope, humanity's most advanced infrared observatory, has revolutionized our view of galactic colors. By peering through dust clouds that block visible light, it reveals the true structure of dust-shrouded galaxies. In the famous Phantom Galaxy, NGC 1618, Webb shows us the delicate filigree of dust lanes and star-forming regions with unprecedented clarity. The infrared view penetrates the obscuring dust, turning dark lanes into glowing structures that trace the galaxy's gravitational field lines. What appears as absence in visible light becomes presence in infrared, a reminder that our understanding of cosmic structures is always shaped by how we observe them. In some galaxies, we can see color changes happening in almost real time, at least on cosmic scales. When galaxies collide, the interaction often triggers bursts of star formation visible as blue patches where new stars are being born. As these massive blue stars live fast and die young, the regions gradually shift back toward redder colors over millions of years. By studying these color changes, astronomers can reconstruct the history of galactic encounters, reading the story of cosmic collisions written in the language of light. Perhaps the most important color story in galactic astronomy involves something we cannot see at all. Dark matter, which makes up roughly 85% of all matter in the universe, emits no light of any kind. Its presence is inferred from its gravitational effects on visible matter. The rotation curves of spiral galaxies, the way their outer regions orbit much faster than can be explained by visible matter alone, provide some of the strongest evidence for dark matter's existence. This invisible component shapes the visible colors we observe by determining the galaxy's overall structure and star formation history. Imagine holding a photograph of someone you love, taken decades ago. The image captures a moment long past, preserving it against the flow of time. Now imagine that photograph taking millions of years to develop, the light traveling vast distances, before finally creating its image. This is the reality of observing distant galaxies. We do not see them as they are, but as they were when their light began its journey toward us. Tonight, we explore this profound connection between light, distance, and time. When you gaze at the Andromeda Galaxy with your naked eye, that faint smudge of light left its source 2.5 million years ago. The photons entering your retina began their journey when our human ancestors were just learning to use stone tools. In the time it took that light to reach us, humans evolved, Civilizations rose and fell, and we developed the scientific understanding necessary to comprehend what we were seeing. The Andromeda we observe tonight no longer exists. In its place is a galaxy that has continued to evolve for 2.5 million years beyond what we can currently observe. This delay between emission and observation grows more profound as we look deeper into space. The beautiful whirlpool galaxy, Messier 51, appears to us as it was 23 million years ago, when Earth was in the Miocene epoch and the first apes were beginning to appear. The Sombrero Galaxy shows us its striking silhouette from 29 million years in the past. And the light from the Pinwheel Galaxy has been traveling for 21 million years to reach our telescopes. For galaxies in the Virgo cluster, our nearest large collection of galaxies, the light has been en route for about 50 to 60 million years. When these photons began their journey, dinosaurs still walked the Earth. The light we now collect in our telescopes left its source long before any human ancestor looked up at the night sky. It has crossed a gulf of not just space but time, carrying information about cosmic structures that may have dramatically changed in the intervening eons. As we peer deeper into the universe, we look further back in time. The galaxy cluster Abell 2218, visible as a collection of reddish smudges through powerful telescopes, appears to us as it was 2 billion years ago. The light began its journey when Earth's atmosphere was just beginning to fill with oxygen, and single-celled organisms were the most complex life on our planet. The galaxies we see in this cluster have continued to move, evolve, and change for 2 billion years beyond what we observe. Some may have collided and merged. Others may have been torn apart by gravitational interactions. What we see is a cosmic snapshot, frozen in the amber of light's finite speed. When astronomers use the Hubble Space Telescope to capture images of the most distant observable galaxies, they are looking back more than 13 billion years. The light from these ancient systems began its journey when the universe was less than 5% of its current age, just 400 million years after the Big Bang. These aren't just distant galaxies, they are time capsules from the cosmic dawn, showing us how galaxies looked when they were first forming. Many of these early galaxies appear small, blue, and irregularly shaped, quite different from the majestic spirals and ellipticals we see in the nearby universe. They show us a time when the cosmic rulebook was still being written, when galaxies were young and unsettled. The James Webb Space Telescope has pushed our vision even further back in time, revealing galaxies that formed less than 300 million years after the Big Bang. These infant galaxies challenge our understanding of how quickly structure can form in the universe. They appear surprisingly bright and well-formed for such an early epoch. The light from these galaxies has spent more than 13.4 billion years crossing space, meaning we see them as they were when the universe was only about 2% of its current age. In the time since that light began its journey, these galaxies have had more than enough time to transform beyond recognition or even to be consumed by larger systems. This connection between distance and time creates a unique phenomenon in astronomy. Rather than seeing a universe where all objects exist simultaneously, we observe a cosmic timeline, with distant objects appearing progressively younger as we look deeper into space. The nearby Andromeda Galaxy appears relatively mature, while the most distant galaxies visible to our telescopes are cosmic infants, newly formed and still taking shape. It's as if we could look across a city and see its history unfold before our eyes, with modern buildings nearby and ancient structures in the distance. The cosmic horizon, the limit of our observable universe, is not just a boundary in space but in time. Beyond this horizon, approximately 46 billion light-years away in any direction, lie galaxies whose light has not had time to reach us since the beginning of the universe. They exist, but their light is still en route, traveling through the expanding cosmos. With each passing year, photons from slightly more distant galaxies finally complete their journey to Earth, gradually expanding our observable bubble of spacetime. For some of the most distant galaxies we can observe, the expansion of space itself has stretched their light to longer wavelengths, shifting what was once ultraviolet or visible light into the infrared part of the spectrum. This cosmological redshift means that to see these ancient systems, we need telescopes specifically designed to detect infrared light, like the James Webb Space Telescope. Without such instruments, these time capsules from the early universe would remain invisible to us, their stories untold. The galaxies we observe at different distances from Earth not only show us different epochs in cosmic history, they reveal how galaxies themselves evolve over time. The most distant galaxies often appear small, irregular, and intensely blue, indicating rapid star formation. Galaxies at intermediate distances, those whose light has been traveling for 7 to 10 billion years, show more structure, with spiral and elliptical shapes becoming more common. And nearby galaxies often exhibit the mature, well-defined structures we associate with modern galactic forms. This cosmic timeline allows astronomers to piece together the life cycle of galaxies, from turbulent birth to stately maturity. Sometimes, the light from distant galaxies passes near massive objects on its way to Earth. The gravity of these intervening masses can bend and magnify the light, creating cosmic mirages called gravitational lenses. These lenses not only distort the appearance of background galaxies, stretching them into arcs and rings, but they can also amplify their brightness, allowing us to see galaxies that would otherwise be too faint to detect. This cosmic magnifying glass gives us glimpses of galaxies even further back in time than would otherwise be possible, expanding our window into the early universe. One of the most striking examples of light's journey through time can be seen in galaxy cluster Abell 370. In this massive collection of galaxies about 4 billion light-years away, the combined gravity of hundreds of galaxies bends light from even more distant sources behind it. The result is a spectacular array of arcs and streaks, each one the distorted image of a galaxy even more distant than the cluster itself. We see the cluster as it was 4 billion years ago, and through its gravitational lens, we see even more ancient galaxies as they were up to 13 billion years ago. It's a cosmic time machine, allowing us to peer into multiple epochs simultaneously. The galaxies we have explored together exist at distances so vast that even at the speed of light, it would take millions or billions of years to reach them. They will forever remain beyond our physical touch, known to us only through the messages carried by light across the immensity of space. Tonight, we explore how astronomers have developed instruments that extend our vision far beyond human limitations, allowing us to study objects we can never visit. For most of human history, our knowledge of the universe was limited to what we could see with our naked eyes. Even the nearest large galaxy, Andromeda, appeared as nothing more than a faint smudge in the night sky. The true nature of galaxies remained unknown until the early 20th century. It was only with the construction of large telescopes and the application of spectroscopy that astronomers could prove these spiral nebulae were actually vast collections of stars lying far beyond our Milky Way. The human eye, remarkable as it is, has significant limitations as an astronomical instrument. It can detect only a narrow range of electromagnetic radiation, what we call visible light. It has limited sensitivity to faint objects, and it cannot record what it sees for later analysis. Modern astronomical telescopes overcome all these limitations, extending our vision across the electromagnetic spectrum, detecting objects billions of times fainter than what we can see unaided, and recording everything with exquisite precision. The Hubble Space Telescope, launched in 1990, revolutionized our view of distant galaxies. Orbiting above Earth's atmosphere, which blurs and absorbs much of the light from space, Hubble can capture images of unprecedented clarity. Its mirror, 8 feet wide, collects enough light to see galaxies more than 13 billion light-years away. Over its more than 30 years of operation, Hubble has observed thousands of galaxies in various stages of evolution, from the chaotic structures of the early universe to the mature spirals and ellipticals of more recent cosmic epochs. Hubble's deep field images stand as some of the most profound astronomical observations ever made. By pointing at apparently empty patches of sky and collecting light for days or even weeks, Hubble revealed thousands of galaxies in regions that appeared utterly dark to previous instruments. The Hubble Ultra Deep Field, completed in 2004, showed nearly 10,000 galaxies in a region of sky smaller than a grain of sand held at arm's length. Some of these galaxies are seen as they were just 600 million years after the Big Bang, when the universe was less than 5% of its current age. While Hubble primarily observes in visible and ultraviolet light, other telescopes extend our vision to wavelengths invisible to human eyes. The Spitzer Space Telescope, operational from 2003 to 2020, observed the universe in infrared light. This allowed it to see through the dust clouds that often obscure galaxy centers in visible light, revealing structures hidden from Hubble's view. Spitzer could also detect the glow of cooler objects, including the oldest and most distant galaxies, whose light has been stretched to infrared wavelengths by the expansion of the universe. At even longer wavelengths, radio telescopes like the Very Large Array in New Mexico and the Atacama Large Millimeter, Submillimeter Array in Chile detect emissions from cold hydrogen gas, the fuel for star formation, as well as the synchrotron radiation produced by electrons spiraling around magnetic field lines. These instruments reveal aspects of galaxies invisible to optical telescopes, such as the vast clouds of gas that extend far beyond the visible borders of spiral galaxies, or the powerful jets of particles ejected from the vicinity of supermassive black holes. At the opposite end of the electromagnetic spectrum, space-based observatories like the Chandra X-ray Observatory and the XMM Newton Telescope detect the high-energy radiation emitted by the hottest and most energetic phenomena in galaxies. These include the superheated gas around supermassive black holes, the shock waves from supernova explosions, and the diffuse plasma that fills the space between galaxies in clusters. X-ray observations have revealed that many galaxies harbor surprisingly active cores, where matter falling into central black holes releases enormous amounts of energy. The James Webb Space Telescope, launched in 2021, represents the current pinnacle of infrared astronomy. With a primary mirror 21 feet across, Webb collects more light than any previous infrared telescope, allowing it to see even fainter and more distant objects. Its instruments are cooled to near absolute zero to prevent their own heat from interfering with observations. Webb's unprecedented sensitivity and resolution in infrared wavelengths have already revealed galaxies that formed just 200 million years after the Big Bang, pushing our vision closer to the cosmic dawn than ever before. Modern telescopes do more than just collect light. They analyze it, breaking it down into its component wavelengths to reveal the composition, temperature, and motion of distant objects. This technique, called spectroscopy, allows astronomers to determine not just what galaxies look like, but what they are made of and how they are moving. Every element leaves a distinctive fingerprint in the spectrum of light, a set of specific wavelengths that it either absorbs or emits. By identifying these fingerprints in galactic light, astronomers can determine the abundance of different elements within galaxies billions of light years away. Spectroscopy also reveals the motion of galaxies through the Doppler effect, the same phenomenon that causes a siren to change pitch as an ambulance passes by. Light from objects moving away from us is stretched to longer wavelengths, appearing redder than it would otherwise. Light from objects moving toward us is compressed to shorter wavelengths, appearing bluer. By measuring this redshift or blue shift, astronomers can determine how fast galaxies are moving relative to Earth. This technique revealed one of the most profound discoveries in modern cosmology, that almost all galaxies are moving away from us, and that the farther a galaxy is, the faster it appears to be receding, clear evidence that the universe is expanding. For the most distant galaxies, those more than 10 billion light-years away, spectroscopy has revealed something surprising. These galaxies contain fewer heavy elements than those closer to us. Elements heavier than hydrogen and helium are created in the cores of stars and scattered into space when those stars die. The abundance of these elements gradually increases over cosmic time as more stars complete their life cycles. By observing galaxies at different distances and thus different times in cosmic history, astronomers can trace this chemical evolution, watching as the universe gradually enriches itself with the elements necessary for planets and life. Perhaps the most remarkable aspect of modern astronomical instruments is their ability to detect objects so faint that they would be invisible to the human eye, even with the largest telescopes. The faintest galaxies in the Hubble Ultra Deep Field emit less than 1 photon per square centimeter per hour, reaching Earth. To detect such objects, Hubble had to collect light for multiple days, gradually building up an image photon by photon. This ability to detect extraordinarily faint signals allows us to study galaxies at the very limit of the observable universe. Objects so distant that their light has been traveling toward us for more than 13 billion years. The adaptive optic systems used on ground-based telescopes represent another triumph of astronomical engineering. These systems measure the distortion of starlight caused by Earth's atmosphere, and then deform a flexible mirror hundreds of times per second to compensate, effectively removing the atmospheric blur. The result is images from ground-based telescopes that can rival or even exceed the sharpness of space telescopes. The twin Keck telescopes in Hawaii, each with a mirror 33 feet across, use adaptive optics to study the centers of nearby galaxies in unprecedented detail, revealing the influence of supermassive black holes on their surroundings. Gravitational lensing, while not a human-made instrument, serves as a natural telescope that further extends our vision. When light from a distant galaxy passes near a massive object, such as another galaxy or a cluster of galaxies, the gravity of the intervening mass bends the light rays, focusing them like a lens. This can magnify the background galaxy, making it appear brighter and larger than it would otherwise. Some of the most distant galaxies known have been observed through such cosmic lenses, their light amplified by factors of 10 or more, allowing us to study objects that would otherwise be too faint to detect even with our most powerful telescopes. The galaxies we've seen tonight are gone, or changed, or still shining somewhere we cannot go, but their light has arrived, their beauty has spoken. In silence, across the dark, they found us. Sleep now, knowing the universe is more beautiful than we can ever fully understand. And yet, we try. As our journey through the cosmic gallery draws to a close, we return to a simple truth. Everything we have witnessed exists at distances so vast that the human mind struggles to comprehend them. The nearest large galaxy beyond our own, Andromeda, lies 2.5 million light-years away. The most distant galaxies we can observe are more than 13 billion light-years distant. These objects are forever beyond our physical reach, known to us only through the faint whispers of light that cross the void of space. And yet, there is an intimacy in this distant knowing. The photons that enter our telescopes, or even our unaided eyes when we look at Andromeda on a dark night, have traveled directly from those far realms to us. They have touched both places, both times. They are messengers that connect beings separated by billions of years and trillions of miles, carrying information across gulfs that we can never physically cross. There is something profound in the fact that the universe is transparent. It could have been otherwise. If space were filled with dust, or if light could not travel unimpeded across the cosmos, we would never know of these distant structures. We would be cosmic castaways, isolated on our island Earth, with no knowledge of the vast ocean of galaxies that surrounds us. Instead, the universe allows light to travel freely across its expanse, carrying with it images of places far removed from us in space and time. It is as if the cosmos wants to be known, to have its beauty witnessed. The galaxies we have explored are more than just scientific objects of study. They are works of natural art, structures of such scale and complexity that they humble our human creations. The perfect spirals with their elegant arms, the colliding systems caught in gravitational dance, the cosmic cities of clusters where thousands of galaxies orbit in shared space. Each of these represents a different expression of the same fundamental forces that operate here on Earth. Yet their scale transforms these familiar forces into something sublime. Perhaps most moving is the relationship between galaxies and time. The light from distant galaxies has crossed not just space but time, bringing us images from the cosmic past. When we look at galaxies billions of light years away, we see them as they were billions of years ago, when Earth was young, or even before it existed. This connection between distance and time means that the night sky is not just a map of space, but a window into history, a panorama of cosmic evolution playing out before us. In the course of our journey, we have seen galaxies not as static objects, but as dynamic systems, constantly evolving through interactions with their environment and with each other. Spiral arms wind and unwind. Stars form from clouds of gas and eventually die, returning their material to the galactic medium. Galaxies collide and merge, their original structures gradually transforming into something new. Even the largest structures, the superclusters and filaments of the cosmic web, evolve over billions of years as the universe expands and gravity pulls matter together. Despite this constant change, there is also persistence. The basic patterns of galactic structure have remained recognizable for billions of years. Spiral galaxies today look much like spiral galaxies did billions of years ago, though the specific stars within them have changed. The cosmic web, with its nodes and filaments, was already established when the universe was less than 1 billion years old. There is something reassuring in this continuity, this persistence of pattern amid constant transformation. As you drift towards sleep, consider that you too are part of this cosmic story. The atoms in your body were forged in the hearts of stars that died long before our solar system formed. The iron in your blood, the calcium in your bones, the carbon in your tissues, all were created through nuclear fusion in stellar cores and scattered into space by supernovae or gentler stellar winds. This material eventually found its way into the molecular cloud that collapsed to form our sun and its planets. In a very real sense, you are made of stardust, assembled from elements that have existed for billions of years and have traveled through many different stars, and perhaps even galaxies, before becoming part of you. This connection between the human and the cosmic provides perspective on our place in the universe. We are tiny beings on a small planet, orbiting an ordinary star in one galaxy among trillions. Yet we have developed the capacity to comprehend the cosmos that created us, to understand processes that occur over billions of years and across billions of light years. Through science and imagination, we transcend our physical limitations to explore realms we can never visit in person. In this way, the universe has developed the ability to know itself, to reflect on its own existence through the consciousness of the beings it has produced. The beauty of distant galaxies reminds us that wonder exists at all scales and in all places. From the intricate structure of a snowflake to the perfect spiral of a galaxy spanning 100,000 light-years, the universe demonstrates an inherent tendency toward order and complexity. This cosmic aesthetic surrounds us constantly, though we often fail to notice it amid the busyness of daily life. The quiet contemplation of these distant structures offers a reminder to pause and observe the beauty in our immediate surroundings as well. To see the galaxy reflected in the dewdrop, the cosmos contained in the ordinary. As consciousness begins to fade and sleep approaches, let the images of these distant galaxies become part of your dreams. The cosmic whirlpools of spiral arms, the gravitational dance of interacting systems, the cities of light where thousands of galaxies cluster together. These structures exist whether we observe them or not, turning silently in the darkness of space. Their beauty is not for us, yet we are privileged to witness it, to be among the beings in the cosmos capable of appreciating the splendor of creation. Sleep now, knowing that while you rest, the universe continues its ancient rhythms. Stars form and die, galaxies collide and merge. Light crosses the void between cosmic shores, and perhaps somewhere among the trillions of galaxies and septillions of stars, other beings also look up at their night skies, also wonder about distant structures, also feel connection to the cosmic whole. In a universe so vast and varied, it seems unlikely that we are the only ones to witness its beauty. But even if we are, even if consciousness like ours exists nowhere else, the beauty would remain. The galaxies would still turn their stately spirals in the dark. Their light would still cross the cosmic void. The universe would still be beautiful, whether observed or not. Rest in the knowledge that you are held within this beautiful cosmos, a small but integral part of its ongoing story. The same forces that shape galaxies also shape you. The same elements that form stars also form your body. The same laws that govern the cosmos also govern your existence. You are not separate from the universe, but embedded within it, connected to it through atoms and energy and light. Let this connection carry you toward sleep, toward dreams as vast and luminous as the galaxies themselves. The galaxies we've seen tonight are gone, or changed, or still shining somewhere we cannot go. But their light has arrived, their beauty has spoken. In silence, across the dark, they found us. Sleep now, knowing the universe is more beautiful than we can ever fully understand. And yet, we try.